Hello, every student. Today we are diving into the fascinating world of simple harmonic motion. Maybe it sounds complex, but it simply refers to a repetitive back and forth motion where the restoring force is directly proportional to the displacement. Simple harmonic motion isn't just a textbook concept, it's all around us. Okay, firstly, let's talk about something that absolutely everywhere vibration and oscillation, and finally, simple motion. Seriously, look around. Have you ever pushed a spring? That mass bounces back and forth. And have you ever played guitar or piano? Those strings vibrate to make sound. And thirdly, a spider feels its lunch because its web vibrates. And fourth, the tall buildings and the bridges sway in strong wind or under heavy trucks. Why is this so common? Because most solid things are elastic. Give them a quick push and they will vibrate, at least a little. Even your phone and TV rely on carefully controlled electrical oscillations. Okay, everyone, next, let's dive into the topic of periodic motion, especially the simplest form of it, the motion of a mass on a spring, just like this graph. First, imagine an object moving back and forth along the same path, taking the same amount of time for each oscillation. That's what we call periodic motion. We'll focus on a horizontal spring mass system because many other oscillating motions are similar to it. Let's make two assumptions here. The first one is the mass of the spring is zero, and it is really so light. And the second, the spring is placed horizontally, so the mass can slide on a frictionless horizontal surface. Okay, when the spring is at its natural length, just like this spring, and it exerts no force on the mass. The position of the mass at this point is called equilibrium position. If we move the mass to the left or to the right, the mass has a displacement compared to the equilibrium position. Here, we take the equilibrium position as x equals 0. If we take the right as the positive direction and if the mass is at here, so the spring is stretched and the distance here is the displacement x and it is positive. And if the block is pushed toward the leftward, just like this, so the spring's length is less than the natural length, and this is the displacement, and x is negative. And then the spring will exert a force on the mass. This force tries to bring the mass back to the equilibrium position, so we can call it restoring force. Just like if the block is at point B, and the spring will exert a force to the block and the force is leftward. And if the block is at point A, yeah, the spring will push the block to the right. In most cases, we can assume that the restoring force F is directly proportional to the displacement x from the equilibrium position. So the formula is that F equals minus k times x. And this x is the displacement compared to the equilibrium position. And the minus sign in the formula means that the restoring force is always opposite in the direction to the displacement. For example, if we take the right as the positive direction, when the spring is stretched, just like in point B, the displacement x is positive, but the restoring force is to the left. It is negative direction. When the spring is compressed, x is negative and the restoring force is to the right. So now this force is positive. This formula F equals minus kx is known as Hooke's law. But Hooke's law isn't just for springs. It also applies to other oscillating solid, and the proportionally constant K is the spring constant or spring stiffness constant. Let's see. Let's write down here. Spring constant or spring stiffness constant. And its unit is Newton per meter. Notice that the force F in the formula isn't constant. It changes with position, so the acceleration of the mass isn't constant either. And that means we can't use the equations for uniformly variable motion. So at here, the acceleration can be expressed as A equals F over m. Okay, now let's see what happens when we first compress the spring by a distance x equals minus a. Also, it is compared to the equilibrium position as shown in the position B, and then release the mass on a frictionless surface. The spring exerts a force on the mass, accelerating it toward the equilibrium position. Because of inertia, the mass passes the equilibrium position with a high speed. When the mass reaches the equilibrium position, the force on it becomes zero, but its speed at a maximum Vmax. As the mass moves further to the right, the force slows it down until it stops momentarily at x equals a, as shown in the position C. After that, the motion repeats, with the mass moving back and forth between x equals minus a and x equals a. So the maximum displacement, the greatest distance from the equilibrium position, is called amplitude. We can say amplitude, the symbol A is the maximum, eh? Maximum displacement. Okay. The cycle is a complete back and forth motion from an initial point back to the same point, like from x equals minus a to x equals plus a, and back to x equals minus a. And the period t is the time it takes to complete one cycle. Finally, the frequency f is the number of complete cycles per second, measured in hertz. So the unit of the frequency is hertz. From their definitions, we can see that frequency and the period are inversely related, just like this formula. The f is equal to 1 over period, or the period is 1 over f. For example, if the frequency is 2 cycles per second, then each cycle takes 0.5 seconds. It is the period, and the frequency is 2 hertz. The oscillation of a vertically hung spring is similar to that of a horizontal spring, but because of the gravity, you see, this is gravity. The equilibrium length of a vertical spring with a mass is longer than the natural length. So, for example, this is the natural length and natural L. So the displacement of the block is not extension of the spring. We can see it in the diagram. When the spring is in equilibrium, this position, equilibrium position, the net force is F net is mg minus k times x. So the spring stretches an extra amount of x0 is mg over k to reach the equilibrium. If we measure x From this new equilibrium position, we can directly use the formula F equals minus kx with the same value of k. But attention again, the x in this formula is displacement, not extension. Any oscillating system where the net restoring force is directly proportional to the negative of the displacement, like F equals minus kx, is said to be simple harmonic motion. We can say is SHM. And such a system is called a simple harmonic oscillator. As we saw in the second page of our PowerPoint, most solid materials stretch or compress according to the equation F equals minus kx, as long as the displacement isn't too large. That's why many natural oscillations are simple harmonic or close enough that we can model them using SHM.